So let's take a look at the solution to our last quiz. This quiz covered Skill 3 relations and functions from Skill 3A to Skill 3D, I believe. Alright, so use the number line below to graph. This set is given to us in set builder notation. It's the set X such that X is an element of the set of real numbers, and it gives us the restriction that -6 is less than or equal to X, which is less than 0. So that interval I can graph on the number line. Since it's less than or equal to at -6 will be a solid dot. At X equals 0 will be a hollow dot. And in between, all numbers in between. The union is or X is greater than or equal to 4. Here's 4. It's a solid dot because it does contain equality, they underline, and then we shade to the right forever because it says greater. So there is my my graph of this set that they gave us. In problem number 2, they give us the graph and ask us to write the set, but they ask us to write the set in interval notation. In interval notation, it's always the smaller number, comma, the larger number. -4 is one endpoint. But since that's a hollow dot, we do not include -4, so that is a parenthesis. We sometimes say open parenthesis. Then the larger number is 4, and since that's a solid dot, we include it. Here we look at a graph. To find the domain, we're going to come in from the left and see what we hit first from the left. So if I use a straight edge, as I come in from the left, the first thing I hit is a solid point, and for the domain I need the x coordinate of that point. So that point is at 0, -5. Yes, and it's a solid point. Oops. I want the x coordinate for the domain. Then as I move from left to right through the graph, I'm passing through all the points until I get to a +5. Since that is a hollow dot, we do not include that endpoint. Now for the range, I'm interested in the set of y values. And remember, our interval notation is a smaller number, comma, a larger number. So for smaller numbers on y, I come up from the bottom and I hit this point. The y coordinate at that point is a -5. As I move up these, I'm looking at every point on the graph, the y coordinate, and it goes all the way up to this vertex where the y coordinate, the x coordinate is 3, but I'm interested in the y coordinate for the range. Since it's a solid dot, it's passing through there, so this must be a closed bracket. So there's our domain and our range for this graph. When I'm given an equation, let me pause this for a second. Alright, so I paused the video real quick to type this. This is how I always start every problem that asks me about the domain if I'm given an equation. My default answer is the domain is a set of all real numbers. Now, I have two things to consider, however, that may change that. It's a set of all real numbers excluding any values of x that cause division by 0. Well, if I look at this function that they give me, I do not have any variables in the denominator, so I do not have to worry about division by 0. So I don't have to worry about that. Any values of x that cause us to take the square root, or actually any even root of a negative number. I don't have any square roots or even roots, so I don't have to worry about that. So my domain is the set of all real numbers, and writing that in interval notation, we can never ever have a bracket around negative infinity or positive infinity, because that bracket indicates that you're including the endpoint, that you're including a number. Since infinity and negative infinity are not actual numbers, they're abstract concepts, hey, we can't include them as endpoints. Alright, so let's take our answer part of our answer that I've typed up here. In number 5, it gives us a formula. F of x is equal to 3 minus x over x squared minus 4. Well, the domain is the set of all real numbers, excluding any values of x that cause a division by 0. We do have a variable in a denominator, so it's possible that for some value of x, it could result in division by 0. So we come in and we temporarily set that denominator equal to 0 to see if there's a solution to this equation, and if there is a solution, or more than one solution, we exclude those values. If I factor this x squared minus 4, I can factor it to x plus 2 times x minus 2. So I can see that x equals negative 2 will make this factor 0, and 0 times anything is 0. And x equals positive 2 will make this second factor 0. Those two values I want to exclude from the domain, because these two values, if you try to evaluate this function at negative 2, you're okay in the numerator. 3 minus a negative 2, that's a number, that's the number 5. But in the denominator, when I square negative 2, I'm going to get 4. And 4 minus 4 is 0. And I can't, 5 divided by 0 is not a number. Even if I try to get the calculator to give me some number, it's, if I programmed this, it wouldn't just say error divided by 0. This virtual calculator, there'd be like an explosion and saying, no, cannot be done, it would go crazy. So we need to exclude negative 2 and positive 2 from the domain. Now, is there more exclusions to consider? Well, no, because the second thing we think about, is there any square roots, any variables underneath an even radical? And there's not, so I don't have to worry about excluding anything here. So on the set of real numbers, and the set of real numbers is the entire number line, the only numbers that we are going to exclude are negative 2 and positive 2. All of the other numbers are fine. They do not cause any problems. If you pick any other number in one of these regions, shaded regions, then do this arithmetic and you'll find a corresponding output, a corresponding y value. Every x in the domain has to correspond to exactly one y value for this to be a function. So if we describe this, when the arrow is shaded, that's negative infinity. Since negative 2 is excluded, we can't have a bracket, we have to have an open parentheses. And then we have union, because we have a break, and it's either this interval or this interval, from negative 2 to positive 2, or because of this break, we have a union, and then we go 2 to infinity, because the other arrow is shaded, and that's indicating it's going on to the right forever. So there's the domain for number 5. The domain for number 6. Well, let's go back. This is always the way we start the problem, by saying the domain is a set of all real numbers. But we have two exceptions to the rule, two things to consider that might, reduce from the set of all real numbers. Well, any values that cause division by zero. I do not have any variables in a denominator, so I do not have to worry about any input causing division by zero. I do have a variable underneath an even radical, an even square root, a square root. So whatever number this 4 minus x represents, we need it to be non-negative. We need it to be 0 or positive. So if we solve this inequality, to say that 4 is greater than or equal to x is the same as saying that x is less than or equal to 4. Notice the arrow pointed towards the x, the arrow is still pointing towards the x. If I place my variable on the left-hand side, it makes it easy for me to graph this on a number line, and the direction of the arrow tells me which direction to shade. So I know I have the number 4 somewhere on the number line, and since it contains equality, I'm going to make it solid. It's less than, so less than means to the left of 4. That's where 3, 2, 1, so forth. And what's not shaded, 5, 6, so on. Let's shade the arrow to indicate that it's going on forever to the left. So to describe this set, I can't list all the points. There's infinitely many points. So they've agreed upon one way to describe it, and the description that's asked for is interval notation. This arrow being shaded is negative infinity all the way up to 4 and including 4. So that makes sense, because if I plugged in 5 or 6, like 4 minus 5 is a negative number, and I can't do that, but 4 minus 3 is positive, 4 minus 2 is positive, and so 4 minus 4 is 0, and I can take the square root of 0. So my final answer, negative infinity, that has to be an open parenthesis, that's as small as it gets, a smaller number, comma, a larger value. So there's my answer for number 6. For number 7, it's asking us for another domain, and since it's an equation, we start the same way that we did these previous problems. The domain is the set of all real numbers. Now, we have some considerations to think about. Any values of x that cause division by 0. In this problem, I do have an x in the denominator. And if x were equal to 10, 10 minus 10 gives me 0, and the square root is 0. I need to make sure that I exclude the number 10, because that causes division by 0. Now, when I take the square root of this expression x minus 10, the square root, it's okay for it to be 0. So at first some people think, well, I'll make it x greater than or equal to 10. But remember, you already threw out 10. Both of these are things that you're excluding. You're excluding 10. You're also excluding all value. We're keeping. Okay. This we're excluding. But when we solve inequality, that's what we're keeping. Hopefully that hasn't been a source of error. I just realized that the way it's phrased could possibly be a source of error for students first learning this. Because, see, this is what I want as far as numbers for this function. And by saying not equal to 10, I'm avoiding, that's not how you spell avoid, is it? I'm avoiding the value x equals 10. I'm saying that I want x, well, I want this, x, okay, so I do want that. I want to avoid x equal 10, so I'm excluding x equals 10. Since 10 is already excluded, my final answer is that x strictly greater than 10. And on a number line, if this is where 10 is, values that are strictly greater than 10 are to the right. So I need this to be an open parenthesis, not a bracket, because if we tried to input 10, we would get 10 divided by 0, and that is not an output. That is undefined. So that 10 won't have a y value to match up to. Now, any other value is okay. So there's our final answer. Alright. So this function takes the input and it creates an addition problem. And in order to have an addition problem, you have to be adding two real numbers. So we can look at this first term and think about what the domain is for this reciprocal function. Well, we start out thinking it's all real numbers, but because we have a variable in the denominator, we know that we're going to have to throw out 0. So we know that x cannot be 0 or any other number in this first term. You can take the reciprocal, but you can't take the reciprocal of 0. When we take a closer inspection of the second term, is x squared plus 1 ever going to result in 0? And see here we say, well, no, it can't, because the smallest that x squared could ever be is 0. And it would have to be equal to a -1 to cancel this +1. And x squared, you can't find a real number that when multiplied by itself gives you a negative value. That's what introduced and made us expand the set of real numbers to the set of complex numbers. But we're not dealing with complex numbers yet. So, even though I have a variable in the denominator, this term, hey, its domain is all real numbers. So if I'm going to add these two numbers together, I just have to make sure that x is not 0, because I would have 1 over 0 there. If I exclude 0 and I keep everything else, I need to describe this set of numbers using interval notation. So the arrow on the left is -infinity, and we go -infinity up to 0. We have to exclude 0, so it's open parentheses, or our values from 0 to +infinity. Pick any x's that are in either one of these intervals, and guaranteed you'll get a y value. That's our final answer for the domain for problem number 8. For problem number 9, the domain is a set of all real numbers, excluding any values that cause division by 0. We don't have any variables in the denominator, so I don't have to worry about that. Am I taking the square root or even root of a negative number? Well, I don't have any even roots. I have an odd root. This 3 is odd. I can take, we've seen it before, that we can take the square root of negative values. The cube root of -8, -2, because -1 times -1 times -1 is and -2 times -2 times -2 is -8. You can take an odd root of a negative number, and you can even get negative answers. So I don't have any square roots or even roots in this problem. My domain is the set of all real numbers. Now, all this has to do is pass the vertical line test for every point. Well, clearly over here, it's passing because it fails if it intersects the graph more than once. This is the only place that truly makes us think about it. Okay, if these were both solid points, it would fail to be a function. But since this is solid, this point is on the graph. When this as a hollow point, that's indicating that point is not on the graph. So this vertical line is intersecting the graph only once. This is a function. Had it been a solid point down here and a solid point up here, then it would have been a no. But as it is, yes, this is a function. Alright, so we know that the true idea is to solve for y to look and see if any x causes or produces more than one y value. We've seen it through doing these problems that if you have a y variable that has an exponent that's even, when you go to solve that for y, it's going to introduce a plus or minus symbol in your equation. So you're going to have two equations. You're going to have one x that you input. These two equations are going to give you two y values. You have, for a function, every x corresponds to exactly one y value, not two y values. This is not a function. And if you think back in your geometry days, and you think about what the graph of this looks like, x squared plus y squared equals 1 is a circle of radius 1 centered at the origin. And a circle definitely fails the vertical line test. So this is not a function. Now here, the exponent on y is 1. So we can solve this y, we can subtract 3/4, and we look on the left-hand side, we see that we have an x squared. We know that that is a quadratic function, that the graph is a parabola. Because of the negative sign, it's opening downward. We can think about shifting to the right 1/2, shifting down 3/4. But this is a function. In fact, we know it to be a quadratic function. Here we've got an y raised to an odd power. So when we solve for y, we've got the cubed root of the opposite of x, but we can take the cubed root of any real number. So this is a function. Anytime that we see y raised to an odd power, as long as it doesn't have absolute value symbols around it, or as long as it doesn't have another function like a logarithm or something like that by it, we're going to be fine with it being a function. We're going to conclude that it's a function. Y is a function of x. Now here I've got a problem because the absolute value symbols are around the y. I know that this equation would break down to two equations. X equals y minus 1, or x equals the opposite of y minus 1. So in other words, I have a positive y minus 1 here, I have a negative here, the plus or minus for the same x, we're going to have different y values. This is not a function. Normally when you have like here in E, when you have absolute value of x as the parent function, you have v. It looks like a v, a vertex setting at the origin. When you have the absolute value of y, that is opening to the right, and that fails the vertical line test because you have it crosses the graph in more than one place. So all we have with the minus 1 is a shift, you know, of that thing up 1. All right. Here, this is an absolute value function. All right, so they want us to read this graph. So when x is 0, well, here's x equals 0, and if I go up on the graph, here I am at this point, 0, 5. So f evaluated at 0 is 5. So here, the input f of 2, f of x equals 2, here's where x is 2 to be on the graph. Here I'm at this point, so this is 2 comma 1, so that's equal to 1. Now, when I come in and read for part C, it wants me to consider only points on the graph that have a y-coordinate of 5. So if I look at this point, it is 0, 5. It has a y-coordinate of 5. If I look at this point, it's 4, 5. It has a y-coordinate of 5. Since that's a solid dot, I include that in the graph, and that's 5, 5. So I have 3 different values of x that all produce an output of 5. When x is 0, when x is 4, and when x is 5, the y-coordinate guaranteed, if you're on this horizontal line, you have a y-coordinate of 5. So when x is 0, when x is 4, when x is 5, the corresponding y value on this graph, on this piecewise graph, is 5. Now, for what values will it equal 10? Let's go up and think about that. Well, here's the line y equals 10. Every point on this green line has a y-coordinate of 10. We're interested for points that are on the graph. This point is on the graph, and its x-coordinate is 8. Its y-coordinate is 10. That is our only answer because this is a hollow point, and although that hollow point has coordinates 5, 10, that point is not on the graph. So it says for what values of x does f of x, hey, here's our graph f, this 5, 10 is not on this graph. X equals 8 is our only answer for part D. Alright, so here it's a substitution. If we evaluate this function for any input, this function h always creates a fraction. In the numerator, it takes the square root of 9 minus whatever number we give it. It's going to subtract it, it's going to square it and subtract that from 9. In the denominator, it's going to add 3 and then take that numerator divided by that. So we're given the number 0, and we now just want to perform this arithmetic. In the denominator, 0 plus 3 is just 3. In the numerator, 9 minus 0 squared is just 9. And the square root of 9 is 3, and 3 divided by 3 is 1. So we know that h evaluated at 0 is equal to 1. Like we said, h takes whatever number you give it and creates a fraction. In the numerator, it's square root of this quantity 9 minus the input squared. The denominator is the input plus 3. Here, we're inputting a negative 2. Let's input everywhere we see an x, we replace it with negative 2. So let's do this arithmetic. The negative 2 plus 3 is just a 1 in the denominator. And 9 minus, well, negative 2 squared, that's a 4. And 9 minus 4 is 5. So we have the square root of 5 divided by 1, which is the square root of 5. And see, that's what it wanted. It said no decimal approximations. We do not want to come in with a calculator and take the square root of 5. They're not asking us for an approximation. They want an exact value. 2.236, this is real close to the square root of 5, but it's not an exact value because this decimal representation goes on forever. This is the exact value. This is what they wanted, an exact answer. Alright, so here we have what they refer to as a piecewise function. In part A, we're asked to evaluate this function when x is negative 4. So we have to pick which of these three equations we're going to use. Well, on the right hand side here, this constraint tells us what we're going to use. Negative 4 is not bigger than positive 2, so don't use this bottom one. Negative 4 is not between negative 2 and positive 2. Do not use the middle equation. Negative 4 is less than or equal to negative 4. So we're going to use the top equation. But instead of writing x, we replace it with negative 4. And we get negative 12 minus 9, which I believe is a negative 3. So that's our answer. Here, again, we have the same piecewise function, but we're asked to evaluate it at a different value. Negative 1. Negative 1 is not bigger than positive 2. I'm not going to use that. Negative 1 is not smaller than negative 2. Think about your number line. Here's negative 2 and negative 3. There's negative 1. So negative 2 to positive 2 is this region. When our number is in this region, we use the middle equation. So x equals negative 1 is right here, and that's in that region. So we're going to use this middle equation. When g is negative 1, this says to take negative 1 and square it and subtract 1. Well, that's 1 minus 1. So we get 0. Alright. Here, 2. 2 is not bigger than 2. I can't use this one. 2 is not smaller than negative 2. 2 is between, if I come back and steal my graph here, which this said less than or equal to 2. This should have been, you may have been yelling at the video that because this is less than or equal to, I should have had that solid. Sorry about that. I went back to steal it at the picture and found my mistake, and well, it didn't like that. Alright, so I can see that 2 is in that shaded region. 2 is shaded there, so I'm going to, everywhere I see an x, replace it with 2. I've got 2 squared, which is 4, and 4 minus 1 is 5. Four is bigger than 2. So we're going to use this bottom equation, and negative 3 times positive 4 is negative 12 plus 9, and we get a negative 3. Now on this final equation, we have to find the difference quotient. So what this function does, it creates an addition problem with negative 4 times the input plus 1. So let's make this bigger. Let's come in and find the first term of my fraction, because my denominator is just h. That's not going to change. I'm not plugging anything into the function. My denominator is h. This first term, I have to plug in. This x gets replaced with a plus h. So I have negative 4, not times x, but times a plus h. And then the plus 1. That's my first term. Now, for my second term, for this guy, and I remember I'm subtracting it. I'm subtracting this whole thing. And what expression do I have here? Well, the input is a. So I replace x with a. So I have negative 4a plus 1. When I go to simplify this, I distribute the negative 4, negative 4a minus 4h plus 1. I distribute the negative sign. The double negative there makes that a plus 4a, and then this minus 1, all divided by h. Well, I notice that this negative 4a and positive 4a cancel each other out. This positive 1 and negative 1 cancels each other out. Negative 4 divided by h, negative 4h divided by h, and h divided by h, these are factors. They divide to 1. We say they cancel, and our final answer is negative 4.